From time to time in our discussions, we have talked about a boatload of techniques for learning information about graphs. In this segment, we'd like to put those ideas together and kind of let them play together in describing the behavior of graphs. Now, we've come a long way. In pre-calculus, basically our techniques had to do with point plotting, and we were looking for x and y intercepts. We talked about symmetry. We also talked about asymptotes when we discussed rational functions, but that's about as far as it went. We could not identify exact maximum and minimum, relative max and minimum points on a graph. We could not tell exactly where those points of inflection were, but we have some great techniques to decide on those issues now. Here are some things that we've learned about. Here's what we know, both including the calculus part and the pre-calculus part. We can describe or discuss information about x and y intercepts, asymptotes, symmetry, domain and range, continuity, differentiability, maximum and minimum points, concavity, inflection points. We know something about all of these, or we can discuss things about all of these ideas. Now, in putting all of this information together, it's a great deal of stuff in our mathematical toolbox to have to contend with all at one time. So we're going to describe a way of organizing this. We're really not going to learn much of anything new in this section. We're just going to organize the information that we already know, perhaps in a relatively new way. Now let's remember this about first and second derivative, and those are the items, those are the techniques that give us a lot of information about maximum, minimum points of inflection and such things as that. And let's review some of those ideas. That if the first derivative is positive over a certain interval, then the graph is increasing over that interval. If the first derivative is negative over some interval, then it implies that the graph is decreasing during that interval. If the first derivative is either 0 or undefined, then we have the possibility of maximum and minimum points. Now, when this situation occurs, and this is really what we're going to target here in our discussion, that we're looking for the zeros of the first derivative function. That's a kind of a big deal. These are a big deal too, but this is even a bigger deal. So once we discover these, we look over at the second derivative, and we have a max if the second derivative is negative. We have a minimum if the second derivative is positive. Now, when I say the second derivative is negative or positive, I mean at that point, at that particular position, you see. Then we know we have a maximum and a minimum, and we recall that the test for maximum and minimum in looking at second derivative fails if the second derivative is 0 at that point. All right, then our information about second derivative comes into play like this. Aside from this, involving maximum and minimums, we know that if the second derivative is positive over a certain interval, then over that interval the graph is concave up. If the second derivative is negative over the interval, then it implies that the graph is concave down. And if the second derivative is equal to 0 or it's undefined, then it implies that we have an inflection point. So all of these things are going to make a difference, and we're going to organize our work in a particular way in order to describe the behavior of a graph. Suppose we want to analyze this polynomial function. We might begin like this. We might say, well, let's find x-intercepts. We'll replace y with 0 and solve this. So we'll factor, and then the values of x that will cause each factor to become 0 are solutions. So our x-intercepts are at x equals 0 and x equals -4/3. Then for the y-intercept, we know that to determine the y-intercept, we replace x with 0 and solve for y. Well, if these x's are replaced with zeros, it's a trivial matter. Y turns out to be 0. So that's x and y-intercepts. And then we would go to the derivatives, first derivative and second derivative, and determine the zeros for those two derivatives. And it works like this. On this problem, y prime is this, and I got that just from the polynomial function, and then replace the y prime with 0 and solve for x. Well, I'm in factored form here, and we called these critical points when we talked about this earlier. The zeros of the first derivative are critical points. So 0 and x equals -1 Those are critical points. Then let's take the second derivative. Okay, so we're taking the derivative of the derivative, giving us the second derivative. And again, we go for the zeros here, and those zeros are called test values. That's what we called them before. We can call them a number of other names now, I suppose, as long as we know that they're valuable information for our analysis here. But the test values here would be x equals 0 and x equals -2/3. Now, what do we do with this information? Well, we're really targeting these critical points and test values. Now, look at them. It's 0 here, it's -1, here's another 0, and here's -2/3. And think about how these points lie left to right. You see, how do they come at us? Well, let's see. It looks like -1 will occur first, and then -2/3, and then 0. And so we subdivide our x-axis into intervals about those important points. So we make a column like this. Let's think about the interval from -infinity to -1. We're thinking about x in that interval from -infinity to -1. Now consider this special point at -1 and what happens there. Then the next interval is between -1 and -2/3. So we say we want to consider x between -1 and -2/3. Then what happens at this point? Then what's the next interval? Well, it's between -2/3 and 0. So we say we want to consider x between -2/3 and 0. Now let's consider what happens at 0. And then what happens after 0, to the right of 0, that means with x between 0 and infinity. So we have subdivided our x-axis into intervals and those special points. Okay, now what we do is we evaluate what's going on with the function, the first derivative, and the second derivative within those intervals and at those special points. Now, for the first and second derivatives, all we care about is positiveness and negativeness. We're not too concerned with exact values. So the analysis can happen very quickly. Now, for the function, we really want to know the value of the function at these special values, at these special positions or points. So when x is -1, y is -1. When x is -2/3, y is -16/27. When x is 0, y is 0. Okay, and I've left all the other parts blank here in this column because we don't really care. We're going to describe what's going on with the function or the graph of the function within that interval using the other information. Now, to analyze the other parts, now notice I have minus, plus, 0, plus, and so on. And the way we get that is that for the values within this interval, and we can just choose a value in the interval and pop it into the first derivative function and decide about whether the first derivative function is positive or negative. It happens to be negative within this interval. The first derivative is exactly 0 when x is -1. In this interval, the first derivative is positive, and so on down the line. So you see how we're building our information. And then again, we want positiveness and negativeness basically in the intervals for the second derivative, and we want to know something about the value at the particular points. So then we can make some decisions about the behavior of the graph within the intervals and at these special points just by looking at this chart. So let's go through and do that. Now, when we see this interval, here's an interval in which the first derivative is negative. Now, if the first derivative is negative in an interval, we know that the graph is decreasing in that interval. All right? We also know that if the second derivative is positive, that the graph is concave up. Then, let's see, so that's what's happening in that interval. The graph is decreasing and it's concave up. Then we have a point at which we have -1 for the function, and y prime is 0. Now, bing, 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 this is the candidate for relative maximum or minimum. We want to test to see if we have a max or a minimum. This is a 0 of the first derivative function. Very important point on the graph. It's where the graph takes a turn either down or a turn up. Okay, so, or at least we have the possibility of that happening. It doesn't always have to happen. So, but at any rate, we have a 0 of y prime that tips us off. Let's test for max or min. We test by looking over here at second derivative. It's positive. Aha, we have a relative minimum. Okay, now back over here to the next interval. So we have another interval. Over that interval, we have y prime is positive. That means that the graph is increasing over this next interval. And y double prime, or the second derivative, is also positive, and that means we're, again, concave up. Okay, now we arrive at the next test point. That point happens to be here on the graph. Doesn't make too much difference until we get to the graph in just a moment, this exact value. But we have a test point. At that test point, y prime is positive, and y double prime is 0. Y double prime being 0 tells us that we have an inflection point. Now, the positive business simply means that we're still increasing. The graph is still going up, but it's an inflection point, and so we're changing our from concave up to concave down at that particular point. That's the value of this information. We're changing from that concave up to concave down. Okay, then in the next interval, we have an interval here, and over that interval, y prime is positive. That means the graph is increasing. So we're still increasing here. We were decreasing at first, and then we started increasing after the minimum, and now we go through an inflection point, and we're still increasing for the graph. But what we have started a little bit of a change, because after that inflection point, y double prime is negative, so we go to a concave down situation, and now we're rising, and we're starting to go concave down. But now what happens? Well, let's see. We have 0 for the graph, 0 for y prime. That makes it a candidate for a max or a minimum, but y double prime is 0, so the test fails. It's not a maximum or a minimum, but the 0 here tells us that we have an inflection point. So we have an inflection point at this particular position, and on to the next interval. In the next interval, we're positive, and so the graph is increasing, and we're positive with y double prime, so we're concave up. Now, so all of this analysis we can do. We can learn all of this about the graph even before we start to construct the graph. Now, when you do your homework, I don't care if you construct the graph before doing this analysis or after you do the analysis. It's okay to do it either way. But it's important to go through the process of the analysis to really analyze those exact positions on the graph where these very important things happen. Now, if you go through the analysis before you construct the graph, then you can construct the graph according to the analysis, and you can do it like this. Now, I have a little graph set up over here, and let's go through and just take one interval at a time. And I'm going to maybe exaggerate some of the ideas from the chart a little bit. In the interval, and I don't mean for you to look back over here because you can't see it, it's a little bit too far over. But the first interval is from negative infinity to negative 1. Here's negative 1. And the first thing I might want to do is identify x-intercepts. I'm looking way over there on the board. I see x-intercepts at x equals 0 and at x equals negative 4/3. That's negative 1 1/3. That's about right here. Okay, so that's an x-intercept. Now, in the first interval, which is from negative infinity to negative 1, so from negative infinity to negative 1, the graph is decreasing and it's concave up. So the concave up idea tells me whether to draw the graph like this, concave up, or whether to draw it like this, concave down, you see. So that it's the tip-off that I want to draw it kind of like this. Now, the next point that I want to plot is at x equals negative 1. And let's see, when x is negative 1, y is negative 1, so that's the point right here. So in that interval, from negative infinity to this point, the graph is decreasing and it's concave up. So the graph then is doing something like this. I'm trying to exaggerate the situation, and it's hard for me to do. Okay, so I have a minimum right there, And that's what the next, I have a relative minimum at -1. The next idea in the next interval, is from -1 to -2/3. -2/3 is about right here. F of -2/3 is -16/27, and that's about right here. And in that interval, in this little interval, you see, we're saying that we're increasing and we're concave up. So we're still kind of going like this. All right, and then an inflection point occurs right here. And in the next interval, which is between -2/3 and 0, we're increasing, but we're concave down. So at that point is where we turn back this way, and you see we're concave down in that next interval. And then there's an inflection point here at 0, 0, and after that we're increasing and concave up. So we're going to go up, and we're going to be like this. So we go through this kind of behavior. Anyway, that's what the overall analysis can do for us. And you know, what we're trying to accomplish here in this section is to put a lot of ideas that we have already talked about into some kind of context, to let them play as an orchestra, let them work together to give us an overall analysis of a function. Before we start the next problem, I want to mention to you or suggest to you that you look at the examples in the textbook. We don't have the time here on video to show all of the nuances involved in this kind of analysis. And in your book, there are quite a lot of examples that show a lot of variety. So you'll get a broader view of the situation by looking at those examples along with the examples on video. Consider this problem. It's a rational function, and you recall that with rational functions we have a consideration of asymptotes. And the first thing we might do is factor both numerator and denominator and set the expression equal to 0. And recall that the zeros of the numerator would give us x-intercepts, and the zeros of the denominator will give us vertical asymptotes. Now there's a horizontal asymptote consideration as well, and that horizontal asymptote consideration was based upon a comparison of the degree of the polynomial in the numerator to the degree of the polynomial in the denominator. Now the degrees of those two polynomials are the same, and in that circumstance you look at the coefficients of the highest degree term, and those coefficients are 2 and 1. Make a fraction out of that. That's 2 over 1. So we have a horizontal asymptote at y equals 2. We have vertical asymptotes at the zeros of the denominator, and those zeros would be at -2 and 2. So at x equals plus and minus 2, we have vertical asymptotes. The x-intercepts, the zeros of the numerator. Now notice the zeros of the numerator are -3, +3. And y-intercept, the y-intercept is found by letting x take on the value 0 and solving for y. Well, up here, if the x's are replaced with zeros, these terms go out. We have -18 over -4. Negative over negative is positive. 18 over 4, that's 9 over 2, or 4.5. So a y-intercept at 4.5. This is an awful lot of information. Even before we get to the derivatives, we might begin to set up the structure of our graph with this information. Horizontal asymptote at y equals 2. I have started the structure here. Here's the horizontal asymptote. Vertical asymptotes at plus or minus 2. So here are those vertical asymptotes. Now let me add the x-intercepts at plus or minus 3. X-intercepts at plus or minus 3, y-intercept at 4.5. Now, and away we go. Now we're ready to analyze the behavior of the graph along particular intervals. And we're going to decide on those intervals according to the zeros of the first derivative function and the second derivative function. So away we go. We have the first derivative is this, and I'm not going to go through the process of finding the first derivative. You'll have to trust me on this, or go to the side and verify that this is correct. But let's see. Now, the values that cause this first derivative to be either undefined or 0 would give us critical numbers. And the numerator becomes 0, the fraction becomes 0 when x is 0. The fraction becomes undefined for plus or minus 2 for that denominator to become 0. So that's why we have these three critical numbers. And then for f double prime, the second derivative is this. And now we want either zeros or values that cause this to become undefined. And it turns out that there's no way for us to get a 0 here. That is, for a value of x to cause this expression to become 0. Fractions become 0 when their numerators become 0. There's no way to find a value of x that will cause this numerator to take on the value 0. I mean, think about it for a moment. Regardless of whether x is positive or negative, when squaring we get a positive result. And therefore, 3 times that positive number will be positive, plus 4 is still positive, and times negative 20 is going to be negative. So any way you cook it, we can't get a 0 here. If x itself is 0, we have 4 still in the parenthesis, and so we can't accomplish a 0. But we can find values of x that will cause the denominator to be 0. We can find undefined values, so those become test values for the second derivative. Okay, at x equals negative 2 and 2. Now, we look at the critical numbers and the test values. Just look at this grouping. There is plenty of overlap here, negative 2 here, negative 2 here, 2 and 2. So really we have 3 distinct values that we're looking at, and we take them sort of left to right. We're thinking about an interval from negative infinity to negative 2, and then another interval from negative 2 to 0, and another interval from 0 to 2, and another interval from 2 to infinity. And we think about these critical numbers themselves, and we set the situation up in a chart kind of like this. So we think about our first test interval, which is negative infinity to negative 2. And this is just one way to describe that. You could use interval notation here if you wanted to do that. But at any rate, we're thinking about as x falls in this interval, what's going on with f of x and f prime and so on. But we begin by structuring this idea. An interval from negative infinity to negative 2, then negative 2 itself. Then from negative 2 to 0, then 0 itself. Then from 0 to 2, and then 2 itself. And then from 2 to infinity is our last test idea. And now we go through the process of finding f of x, f prime of x, and f double prime of x for these intervals and these particular points. The first thing we'll do is find the value of f of x when the function takes on the exact values of x equals negative 2, x equals 0, and x equals 2. So just go down that column and fill it in. And then go down the next column for f prime of x. And you're just thinking of positiveness and negativeness along the intervals, and you're thinking of exact values for f prime for those 3 values, those 3 particular values that we had earlier. So you fill in that column. And then you fill in f double prime. Just think about the intervals. And again, it's positiveness and negativeness on the intervals and whatever value the function takes on for the specific values for x from that leftmost column. And now we're ready to go through and take a look at the conclusion. So we'll go fill in the conclusion according to what we have. Now really all we need to do is look at we can look at the columns separately if we want to. For example, if we look at this negative along the interval that we were talking about here, and I don't even need to look at it right now. I know that if f prime is negative on an interval, it just tells me that the graph is decreasing. So I can put out here, everywhere I see negative through here, I know that the graph is decreasing. So for these 2 boxes over here, I can say the graph is decreasing. And for those boxes where I have pluses, you see I know that the graph is increasing. So increasing. Now we can analyze these a little bit further because we want to know something about whether they're increasing or decreasing. We want to know something about whether the graph is concave up or concave down. Well, we just slide our attention over in the chart to, oh, okay, the second derivative is negative, you see, and that tells us something about the graph is concave down. And a plus, well, that's concave up. And then a plus, and that's concave up. and then a negative, and that's concave down. Okay, now let's go back through. We've analyzed these intervals as much as we can. It turns out that the blanks here are at those special points. And now we have undefined situations for all of these, and that was a position for an asymptote. It's a vertical asymptote. And down here also for these undefined values, a vertical asymptote. Now all that's left to do is to analyze what's going on here. Now, since we have a 0 for f prime of x, this is a candidate for a maximum or minimum point. That's what the significance of f prime of this value means. So a candidate for maximum or minimum. Since we have a positive second derivative, we know it's a minimum. So here's a minimum point. Now, with all of this information, we can go back to the graph and sketch it. Now, I'm going to have to read from over here. Well, let's slide back over to the left to the graph, and I'm going to have to read as we go along. Now, we can all of what I do here can be verified by plotting a few points, and that's really what we did in college algebra or in pre-calculus. We plotted points in this region of the graph and in this region between the vertical asymptotes and in this region of the graph. That's how we decided on the behavior of the graph, and that's a pretty good way of dealing with the situation as well. But and we need some reference for that anyway, you know, somehow or another. Even if we know in this area of the graph that what we know about this is that the graph is increasing and it is concave down. Well, gee, does it do that up here, or does it do it down here? Well, just one point of reference will help us understand how that works. We have a point of reference there that we're going to work with. All right, let's start from left to right. We need some organized fashion here. So we'll start with the left interval. That's from -∞ to -2. That's this part of the coordinate plane. And we know that, let's see, the graph is decreasing and it's concave down. Now, we have a point to work with, and when we were in pre-calculus, the points were what we worked with exclusively. You know, we just plotted a few points to discover the behavior of the graph. Well, now all we need really is one point to know where the graph is this way on the coordinate plane. So let's see, decreasing, concave down, going through this point, and we know something about the idea of asymptotes, that the graph snuggles up to those asymptotes at the extremes of the coordinate plane. So we know that the graph has the behavior like this, close to the asymptote to the left here, and then goes through this point, concave down, and then snuggles up to the asymptote down here. The next interval is, well, the next point is x equals -2. We have that asymptote at that point. Then the next interval is right in here from -2 to 0. And let's see, and we arrive at the next point is at 0, and at 0 we have, I'm looking at the chart now, and I'm seeing that it's a minimum point at this point. So we're coming into that minimum point. Now in this interval we are decreasing and concaved up, and so we have this kind of behavior. And now I realize that some of this information is relatively redundant. That is, several of our instructions here kind of overlap with one another. We know that in this interval, if that's a minimum, then certainly we're going to be next to the asymptote over at this side of the interval, and we're coming down to this minimum point. So we almost have to be concave up. So that's not great news to us. I mean, that's not big news, but it certainly helps us to verify what we thought about the graph. In the next interval, we're talking about, again, concave up, and the graph is increasing. And again, that's not a big mystery to us. If this is a minimum point and that's an asymptote, we kind of know that that's going to happen. In the next interval, we're talking about to the right of this vertical asymptote. The graph is increasing and concave down. So we're talking about in this interval, here's a point, there's an asymptote, here's an asymptote, no big deal to understand that the graph has this behavior. We're going to look at the graphical relationship between functions, derivatives, first derivatives, and second derivatives now. We can get a clue as to how their graphs relate, and we looked at it before, but we can get a clue about that by thinking about polynomial functions. Now, you know that the graphs of polynomial functions just have this curvy kind of continuous graph that we're so familiar with. And in pre-calculus, we studied about how many curves there could be in, let's say, a fifth-degree polynomial function. How many curves could there be? Well, there can be as many as 5 x-intercepts on a fifth-degree polynomial function, and so there would be 4 curves. And then what about derivative? Well, when we take the derivative of a polynomial function, we have a polynomial function whose degree is 1 less than the degree of the one that we started with. And then the second derivative would be 1 less degree than that. And so you can think about how the graphs would look when you think of that decrease in degree of a polynomial function. Now think about that in terms of this function. Here's the function f, and here is its graph. Now let's try to structure or think about the first derivative and second derivative functions and lay them on top of this. Now we know this about first derivative. We think about it, well, let's see, it's talking about, or it describes the slope of the tangent line. Well, what about a tangent line at this point, this point, this point, this point? Well, we know those tangent lines are negative, so f prime is going to be negative in this part of the coordinate plane. And f prime right here, that tangent line is exactly 0. So f prime is going to be 0 at that point, you see, because it's the slope of the tangent line at a point. That's what f prime is all about. So it's 0 right here, and it was negative before. So it's going to come up like this, something like this along this interval. Now where is it going? Well, let's see. The slope is increasing here, and it's getting to be a bigger and bigger slope. That just means that this value is coming up, 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 and then it comes up to a point of, let's see, inflection, and let's say the inflection point is, I'm guessing right here. Now that inflection point simply means that at this place, the slope of the tangent line stops the increase and starts to decrease, and that means that there is a top to it. There is a spot where there's a maximum. And you know what I ought to be doing is, let me get an eraser. I ought to be making this a dotted line, and I think I'll make it dotted like this so we don't get them confused. Okay, so the graph is coming up. It goes to this top point. Now, at this maximum, the slope of the tangent line is 0, and that gives us a 0 for f prime. So now we were getting a picture of f prime. The f prime goes up here. It's got a max, and it's coming down to this point, okay? And then it's negative. The slope is getting to be negative here, negative, 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 negative. Okay, so this graph then has this kind of behavior. Now, from an algebraic standpoint, we have an f function that has 3 x-intercepts, and it appears to be going without bound, or rising without bound to the left and dropping without bound to the right. And so it's a third-degree polynomial function, and no wonder its derivative is a second-degree polynomial function. It's just a quadratic equation. Okay, and so our graph is a parabola. Now, when we take that quadratic equation, or the graph of it, and we perform derivative on it, what do we get? We go from a second-degree polynomial function to a first-degree polynomial function, a linear equation. So the graph of f double prime is going to be a linear equation. Let's see if we can describe that. All right, I'm going to label this f prime, you see, for the parabola. Now, what about for f double prime? Well, let's see. We're talking about slope of tangent line now, and we're thinking about, let's see, we're increasing up to this point. Now, what I'm doing here in making this analysis is I'm thinking about the slope of the tangent line of that graph. That's what I'm concentrating on, and that helps me think about where the graph is going to be located or where it's going to cross. We have a maximum here, which means that the slope of the tangent line at that point is 0. So we have a 0 then for f double prime. All right, and here that it's positive. Let's see, the slope is positive through here. It's a big positive number here, and it's a small positive number here. It kind of looks like it'll start up here, big positive number, and a smaller positive number through this interval. So that's how its behavior is. And if we know that it's a linear function, then we know that it's going to have this kind of behavior. And it fits with the rest of the graph too. It begins to go negative here, small negative number, bigger, 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 because the slope is getting steeper, steeper, steeper. So that's why this continues to go down in this fashion. All right, let's go through another analysis. And this time, let's start in the middle of the analysis. Let's start with the derivative function. So let's say that here's the graph of f prime. So we have a linear function for f prime. Now, we can go in either direction first if you want to. We can go to the f double prime function, or we can go to the f function. Let's go to the function itself and think about what the function needs to look like. Now, if it turns out that in going the other way, if with polynomial functions we take a derivative and we have a function that is of one less degree, and then the f double prime is one less degree than that, then going in the other direction we increase degrees. So here we have a first degree function, and when we go to f, the f function then would be second degree. So it's going to be a parabolic curve. All right, where does the parabolic curve have significant points? Particularly, where is the maximum or minimum point? And do we have a maximum or a minimum here because of this graph? We should be able to tell. Well, let's see. We have a certain slope here, and we have a 0 right here. It looks like the origin. I tried to make it at the origin anyway. Let's say it's at the origin. And so we have a 0 of f prime, and that means that the slope of f is 0 at that point. That means we have a maximum or a minimum. Now, from left to right, we have, let's see, negative values for f prime means that the slope of f is negative in this interval. The slope of f is negative. That means the slope of f, that means it's coming down like this. You see now, so it's coming down, and it reaches this point where the slope of the tangent line is 0, and then the function is increasing through here, so away we go. So it's going to have this kind of behavior. Now, where does it cross? We don't really know. This only tells us things about the graph having this behavior. It doesn't tell us where it's located on the graph up and down. So maybe it passes through right here, let's say. And so the graph then once again, I went and made it a solid graph, but that's okay. We'll call, here's f. Now, what about f double prime? Well, we can decide on the second derivative by looking at the first derivative function. And remember that the second derivative is just the slope of the tangent line of this. Well, gee, this is a straight line. The slope is constant. Then the graph of f prime, double prime is constant. You see, it's just a constant function. And if this is, let's say it's a slope of 2, then what we'd have for f double prime is a constant function like this. Okay, so if f prime is linear, that implies that f is quadratic and that f double prime is constant. All right, and sort of the converse would be true too. If f double prime is constant, then it would imply that f prime is linear and that f is quadratic. Okay, let's keep that in mind because we're going to look at another one. Now, in this one, we have information about f prime, and notice that f prime changes from one interval to another on the coordinate plane. We're going to consider this interval, we're going to consider what's happening in this interval, and consider what happens over here. And we want to construct the graph of both f and f double prime. All right, let's construct the graph of f first. All right, if we have a constant on this interval, that just now for f prime, that means that the slope of the tangent line of f is constantly 2. Constantly 2. So the slope is constantly 2. That means that f is a line whose slope is 2 in that interval. Now we don't know, and here's f, and here's the interval we're talking about from negative infinity to negative 1. So in this interval, the slope of f is 2. Now that means that it has this kind of behavior, but we don't know if it's here or down here or up here. We don't quite know where it is on the coordinate plane, but we just know the slope is 2. So it could be that it's here, and I want to, let's see, that's a slope of 2. Okay, now, next interval. So in this interval, let's see, we have f prime is, has a slope of 2, and it's negative, f prime is negative here and positive here and 0 here. Well, 0 for f prime means, let's see, means the slope of the tangent line at a point is 0. That means we have a max or a minimum at this point. And because we have negative, we have a negative slope for f along this interval, negative slope, that means the graph is falling. So the graph is falling, decreasing in this interval, minimum, increasing in this interval. So along that interval, and again, we don't know where up and down this is occurring, but we do know that we have a situation where the graph goes down and has a minimum and then comes back or increases in that next interval. So we would have something like this. We just know that there's a minimum at 0, and again, this could move down, shift up, or down on the coordinate plane. All right, then again out here, for if f prime is constant, then it means that f is has a linear graph, a straight line graph, and it has a slope of, let's see, 1, 2. So the slope of that graph is 2, and we again don't know quite where it is. Maybe it's the end point is here, and let's see, a rise of 2 and a run of 1. I'm just trying to get the right structure to it, and here we go. So it would do something like this. Okay, so that's what f is all about. This is one structure for f. There are a lot of other structures for f, but they'll look pretty much like this. It's just that they can be shifted up and down on the coordinate plane. All right, now with this idea of f prime, what about f double prime? Okay, f double prime. Now what we think about here is the derivative of f prime. The slope of the tangent line. Let's think of slope of tangent line for in each interval. Well, the slope of this tangent line is, it's a slope of 0. So f double prime is going to be 0 in this interval. That means, here's f double prime. That means from negative infinity to this point, f double prime is 0. Now what about the next interval? In this interval, let's see, the slope is a constant 2 in this interval. So from negative 1 to 1, f double prime is a constant 2. So f double prime is a constant 2. And then in this interval, let's see, the slope of this line, the slope of the tangent line along this interval is going to be 0 again, you see, because it's flat. So let's see, 0 then from here on out to positive infinity. And the others are left for you for homework.